that much help for this stuff. All right, so this is a year 12 pre-learning lesson. So there's a couple of things in year 12 that you need to remember, like from year 11 and probably from high school too, that most of you guys probably haven't remembered that well. So we're going to start off with a revision on options 3. I'm pretty sure everybody remembers their options 3. So we're going to start off with modular arithmetic. Modular arithmetic. I don't know how to spell it, so we're just going to say that's it. Anyways, so we're going to start off with an analogy with a clock. So over here I have a clock, right? And I think I've used this analogy before, but this analogy is the best way to make sure people understand what's happening with the modular arithmetic. So let's have a look. So basically, right now, everybody can see that the time is 9 p.m., 9 a.m., whatever it is. Now, if I asked you, what's the time 6 hours later, right? So right now the time is 9 p.m., let's say. What's the time 6 hours later? Right? So 6 hours later, we would say that the time is 3 a.m., right? But we know that 9 plus 6 does not equal 3, right? So what's actually happening? So what's happening is you can see that 9 plus 6 doesn't equal 3, but if you divide 9 plus 6 by 12, which is how many hours there are in a day, the remainder is 3. So you can see over here, 9 plus 6 is equal to 15. 15 divided by 12 gives a remainder of 3, right? And if we have a remainder of 3, we know that that's the time, right? So we can see clocks work in modulo 12, right? In mod 12. Because when you divide the total addition by the mod you're working in, the remainder you get has to be less than or equal to 12, right? So let's have a look. Let's have a look at some other examples, not just modulo 12. So remember, we're only focusing on the remainder, and this is just a quick little brief understanding, reminder of what modulus is. So over here, let's say 34 is congruent to what mod 5? I'll ask Raja. Raja, what is 34 congruent to mod 5? Okay, I guess he's dead. Omi, what's 34 congruent to mod 5? Oh, he said it. Okay, 4. Sure. Okay, so 34 is congruent to 4 mod 5 because when you divide, all right. When you divide 34 by 5, your remainder is 4, right? So that's why we get it's congruent to 4 mod 5, right? And the reason that we do this is because it's mathematically the most simple way to express it. So 34 is congruent to 4 mod 5 because when you divide by 5, the only remainders we can have are 0, 1, 2, 3, and 4. And this is an important fact that most people don't understand completely. And I'll show you why. Because in this example over here, minus 8 is congruent to what mod 5, Daksh?
Minus 8 is congruent to what mod 5?
Yeah.
I'm guessing it's probably what? Negative. I'm not fully sure.
All right, that's all right.
Yeah.
So basically, if you think about it, right, let's just consider this instead of minus 8, let's consider it 8, right? So 8 is congruent to 3 mod 5 because the remainder when you divide 8 by 5 is 3, right? So we could say that minus 8 is congruent to minus 3 mod 5. But remember, we said in modular the only remainders we can have is 0, 1, 2, 3, or 4 because a remainder of minus 3 makes no sense, right? So if you think about it, 5 is congruent to 0 mod 5, right? Because dividing 5 by 5 gives you a remainder of 0. So what I'm going to do is I'm going to add 5. And why can I add 5? Because this is 0 in mod 5, right? This is congruent to 0 in mod 5. So I can add 5 on one side without changing anything. So it's mod 5, right? And so over here we get minus 8 is congruent to 2 mod 5. Does that make sense, Daksh? Hopefully.
Yeah, that makes a lot of sense.
All right, cool. So although this is mathematically correct, This is mathematically correct. We want the answer as a positive integer because remainders tend to be positive, right? Now, I'm going to give you guys a question, and let's see if you guys can do it. So I'll give you a couple questions. So one of them is minus 10 is congruent to what mod 4? And minus 7 is congruent to what mod 9? Alright, I'll give you guys a minute. मामा ये खुला हुआ दरवाजा मुझे बहुत तंग कर रहा है मैं बंद करूं just probably type like 1 into the year 12 options chat. Can you all type 1 when you're done? Because, yeah. Okay, everybody's done. All right, so, Raja, what did you get for the first one?
Yeah, is it working?
Yeah, it's working, it's working. What did you get for the first one?
I'm not sure, is it 2?
2. All right, let's have a look. So we'll quickly have a look at what Raja did. So we can see over here minus 10, when we divide it by 4, the remainder is minus 2, right? Yes? So let's have a look. We get minus 2 mod 4. And if I add 4 on both sides, I do in fact get 2 mod 4. Now, okay, so that's that. So, Dux, what did you get for the second one?
Is it 2 mod 9?
Yeah, it is 2 mod 9. So, minus 7 is still congruent to minus 7 mod 9. Now, why I did this is because if you divide minus 7 by 9, your remainder is still minus 7, right? Because you haven't gotten a complete, you haven't got any number greater than 9 there. So, again, we can just add 9, so we can get 2 mod 9. Now, there is actually a hack to this, okay? So there is a hack to this. Instead of doing a 2-step process, we can do it in 1 step, okay? So the way that you do it in 1 step is, let's consider another example. Let's do minus 11 congruent to what mod 4, right? So basically, all I'm going to do is I want you to count backwards. So you're going to have to count backwards from minus 11, sorry, to the first number divisible by 4. Whoops, that's bad handwriting. So what I mean by that is from minus 11 we count backwards. If we just count backwards 1, we get minus 12, right? And minus 12 is divisible by 4. So we actually counted back just 1, right? So it's congruent, minus 11 is congruent to 1 mod 4, right? So let's just do the previous example. Minus 10 is congruent to what mod 4? So minus 10, we go to minus 11, and then we go to minus 12, right? And so we counted back 1, 2, right? So we counted back 2, which means that it's congruent to 2 mod 4, right? So if you count back, you should be able to do it really, really quickly. Same thing with the minus 7 is congruent to what mod 9? Minus 7, you go to minus 8, and then you go to minus 9, right? So you count back 1, and you count back the second. So there's 2, so minus 7 is also congruent to 2 mod 9. Does that make sense? So I'll quickly give one last example that's slightly trickier. Minus 1111 is congruent to what mod 759? So I'll give you guys like 1 minute to work it out. Just to type 1111 when you're done. Yeah, Frank, you might need what do you call it? You're gonna need cost. Do you have cost?
Yeah, I already have it.
Did you get the link for the party?
Yeah. Hold on, I'll click on it now.
Yeah, so you have to request. You have to send me a request.
Wait, can you send it again?
Yeah,
I can't find
sure,
out
sure.
five.
I can send it again. Just give me a second.
Mhm.
Invite. Copy. Should I just DM that to you, or do you want me to?
Yeah.
I'll just put it on the chat. It's in the.
Mhm.
If you click on the year 12 options chat in the Discord, you should see it.
Yeah.
Yeah, cool. All right. How does it feel being in year 12, boys? Tough work, huh? All right, nobody's done yet. Oh, all right, you're done. Okay, cool. I'll just wait for one more person to be done. Oh, cool.
I sent my request.
Yep, got it. All right, so now you just join. Yep, so now you just join. Is anybody else done? I don't know. All right. Dux, what did you get?
I got 407
Yeah,
mod
perfect,
759.
perfect. So so basically, so this one is a little bit more tricky because it's a lot bigger, right? Like the numbers are a lot bigger. So you need to use your calculator. So in this one you need to use your calculator. So I'll teach you how to use your calculator. Now over here, there's a couple things that you need to know with your calculator. So on your calculator, what you do is you write 1111 over 759, right? And then there's this button on the calculator. It looks like this. It's got an S to D, right? And you press your shift button, which is up here, right? You press your shift button and then you press this button after you click answer. So what happens is it converts this to 30, so it converts this to 132 over 69, right? So over here, 32 over 69. So over here you can see that it's 32 over 69. And if you make 69 759, so you multiply top and bottom by 11, you get 352 on 759. So you can see your remainder is 352, but it's actually minus 352, right? So it's minus 1111 is congruent to minus 352 mod 759, right? And then what you do is you basically just add 759 and you get 407 mod 759. Cool? So hopefully that makes some sense. However, it does get slightly more harder. I'm pretty sure that over here everybody at some point here has done modular arithmetic equations, because that's also a part of something that we have to know how to do. So for this we need a little bit of options 3 as well. So let's just do solving modular congruences. Okay, so solving modular congruences. So what I mean by that is I'm going to put up one equation and I'm going to go through the example. So 4x is congruent to 8 mod 5. So what I'm saying, so basically what this question is asking is, what does the value of x have to be so that it's congruent to 8 mod 5, right? Or in other words, 8 is congruent to 3 mod 5? Or in other words, what does the value of x have to be so that this leaves a remainder of 3, right? So let's try solving this. So obviously to solve a modular congruence, it needs to be done like algebra, right? But I can't divide both sides by 4. So instead we have to multiply both sides by what, Raja? Raja, do you know what we have to multiply both sides by? Or I should say pre-operate.
Sorry, multiply both sides by.
Yeah, what do we have to multiply both sides by?
Hello, can you hear me?
Yeah, I can.
Hello?
Yeah, I can hear you.
See, you're talking, but I can't hear.
Huh? Oh, wait. Alright. Just to type it. Do you know what it is? Okay. Can you hear me now?
Wait, Amma, can you go back up so I can take a screenshot?
Oh, yeah, sure. Over here. I'm
Wait.
recording this, so... Wait, can you hear me now, Raja?
Yeah, I can.
Alright, cool. So, do you know what it is? What you have to multiply both sides by?
See, the way I was gonna do it was just solve 8 mod 5 is 3, so 4x is equal to 3, so x is 4.
X is 4. Is that what you say?
No.
Oh, okay.
Hold on. So 8 mod 5
Yep.
is congruent to 3, right?
Yes.
So 4x is equal to 3.
4x is equal to 3. Oh, okay. It's close. So...
And then x.
Yeah, I get what you're trying to say, but what we do is we sort of take this like an options 3 question, right? So this is like an options 3 question. Okay. So if I told you that this was like your pre-operate, post-operate sort of questions, what you're doing actually is you're multiplying by 4 inverse on both sides, right? Because you want to get rid of that 4, don't you? You want to make this total thing 1. So, and you get a 4 inverse times 8 mod 5, right? So over here, let's figure out what 4 inverse is. So, Umi, how do you think we would figure out 4 inverse?
Wouldn't it just be like 1/4 since it's multiplication?
No, see, it's not, because it's under a modular, right? Remember, modulus, we can't have fractions. We went, remember, because it's only about remainders.
Yeah, then I'm not sure.
All right, so what we know is 4 inverse multiplied by 4 must equal 1 in mod 5. Yes? So what we can see is, let's just try some values, right? So if 4 inverse is 1, then we just get 4 mod 5. But if it's 2, we get 8 mod 5, which is congruent. So over here, let's try 4 inverse. Let's say it's 1, right? So we get 1 times by 4 is congruent to 4 mod 5. So that's definitely not it, right? 4, if we say 4 inverse is 2, then over here we get 8 is congruent to 3 mod 5, right? So that's definitely not it. If we say 4 inverse is equal to 3, then over here we get 4 times 3, 12 is congruent to 2 mod 5. And if we say 4 inverse is equal to 4, we get 16 is congruent to 1 mod 5. So we know that 4 inverse must be 4. So 4 is a self-inverse basically. So if we multiply by 4 on both sides, we get 16x is congruent to 32 mod 5, right? And this obviously under mod 5 is just 1. So x is congruent and 32 is 2 mod 5. So x is 2 mod 5. Does that make sense for me?
Yeah.
Yeah. All right, cool. So let me do one more example and then I'll give you guys a question to try. So one more example is 4x is congruent to 2 mod 5. Now for this one, I'm going to do a little bit of a cheeky thing. So what I'm going to do is I can see 4x is the same thing as saying 5x minus x is congruent to 2 mod 5. And everybody knows that since this is 5x, we know that this must clearly be 0 in mod 5. So minus x is congruent to 2 mod 5. X is congruent to minus 2 mod 5. And remember, you just add 5. So x is congruent to 3 mod 5. Okay, so there's two methods of doing it. Now, obviously, this is very, very basic modular equations when we do it in options 4, because we're going to revisit these ones. You have like really, really complex ones, like 4x plus 1 is congruent to 2x mod 5, right? Like these ones are super complicated and they require a lot of like steps. But we're not going to do that yet because we don't have the maths to do them. But the simple ones we can try now. So over here, I'm going to give you guys 30 seconds to try solving 4x is congruent to 3 mod 5. All right, go. Just type like 1 when you're done.
Yo, could you scroll up for a bit just so I can see the other part?
Sorry, you want me to scroll up a bit?
Yeah,
Like
yeah.
this? Or down? Or up? More up?
No, that's perfect. That's perfect.
That's perfect? Cool. Alright. Alright, well, 2 people are done. That's ridiculous. Okay, so 2 people are finished. I'll just ask Umi. Umi, what did you get?
I got x is congruent to 2 mod 5.
Perfect. Okay. And Dux, you got the same thing?
Yep, exactly
Cool.
the same.
Cool. Good. So, again, there's 2 methods to do it. The first method was the one I showed up here, finding 4 inverse, right? That's method 1. And then the second method over here was so it doesn't matter which method you use, you'll get the same answer. So let's just use method 2 because it's easier. 5x minus x is congruent to 3 mod 5. That's 0 in mod 5. We get x is congruent to minus 3 mod 5. And so we add 5. We get x is congruent to 2 mod 5, right? Super simple. So
Just a quick question, Ahmed.
yeah.
Do we need to know both methods for the more complicated questions, or are we fine with the second
Actually, for the more complicated things, I mean, it's good to know both methods because sometimes I can't really predict what's on the exam. But for the more complicated questions, you actually need to know another method called the Euclidean algorithm, which is what we learn later on in options 4. But it is good to know both these methods because it is quite fundamental to solving some of the easier questions. Because obviously you'll get some of the easier modular congruences and then some hard ones too.
Okay,
Yeah.
cool. Thank you.
All right. So that's all for modular congruences. Now I'll go back a little bit to core, or actually to high school, which is we're gonna do some basic probability. And factorials. Okay, so basic probability and factorials, right? So let's start off with some basic probability. So over here, we have tree diagrams. So who remembers what a tree diagram is? Probably not. Okay. So basically a tree diagram, right, is a super simple way of approaching a probability problem. And it's actually super useful because you'll need to know it throughout all of Core 4. And 99% of the time, I can guarantee you that when I was stuck on a Core 4 problem, I would 100% of the time use a tree diagram to make it simple for myself. And even towards the last questions in Core 4, tree diagrams are super important. But nobody teaches you how to draw them properly. So let's talk about the structure of a tree diagram because it's a little bit different to the ones you learn in high school. Okay, so the structure of a tree diagram. So let me draw a general tree diagram. So over here, we have a start, right? And then, whoops, that's a really ugly line. You know what? That's all right. And then so we have event 1, and we have event 2, and then we have like all the way, like, if I just call this event 3, I should probably make this like all the way to event n minus 1 and then event n, right? So So when we're doing a probability, right, we have multiple events that are occurring, right? And this tree diagram is basically showing, is a way of drawing all the possible events that could occur, right? So these are all possible events or outcomes, right? Okay. Now, on the branches of the tree diagram, it's super important to write the probability of each of them occurring, right? Probability of occurrence. So the probability of each of these events occurring is super important to write on the branch of them, and I'll explain why in a little bit. But for now, let's just practice drawing some tree diagrams. So let's do an example. Let's do a coin toss. Whoops. I always write coin toss as one word for some reason. Coin toss. All right? So over here, I'm going to quickly do it for you guys. So a coin toss, right? A coin toss has two possibilities, heads or tails, right? So at our start, we have two possibilities. We have heads and we have tails. And Frank, what's the probability of a heads or a tails occurring?
50, 50 each.
Yeah, 50%, right? And how do we express 50%? We express it as 0.5, right? So we write our probabilities on our tree diagram. So that is the tree diagram for a coin toss, a single coin toss. Now, can everybody try doing oh no, actually no, I'll do one more. So how about a two coin tosses, right? Oh, well, I actually cannot spell coin tosses. Okay, two coin tosses. So over here, let's try. So obviously in our first coin toss, we have heads and then we have tails. Now, let's say after our first coin toss, we get a heads, right? If we get a heads, then we have to do another coin toss because we're doing two and we have a probability of a heads or a tails, right? And again, if we just get a tails, then we have to do another coin toss and we have a probability of a heads or a tails. And again, all of them are 0.5, right? They're all 0.5. The probability of all of them occurring are 0.5. Now, the reason that we write the probabilities on the branches is because of this question right here. What is the probability? So probability is denoted by PR of a heads and a heads. So what is the probability of two heads? So obviously, we start off with 0.5 and then another 0.5, right? So first we need a heads and then we need another heads. So I should probably start changing color. So over here, we need two heads, and the probability associated with this head is 0.5, and the probability associated with this head is again 0.5. So over here, we have 0.5 times 0.5. So our final probability is 0.25, right? Or 1/4. So in 1/4 of our tosses, we would get two heads in a row. So let's try drawing a tree diagram. But however, I'm not gonna make it that easy for you guys, right? So can you guys draw? So I'll just write it in like what color should I use? I'll use red. Draw tree diagram, and make sure you guys give a lot of space for this because it's a big tree diagram. Draw a tree diagram. Oh, whoops. For two dice rolls. Okay, so two dice rolls, and remember, dices are six-sided, right? And they're remember, it's a fair die. We're assuming that everything is fair here. It's six-sided, so it has possibilities 1, 2, 3, 4, 5, and 6. So I'll give you guys a minute to draw the tree diagram. Can you type a 1 when you're done? Alright, so just one person is done. Give everybody some time because this takes a while. I'll just start drawing it really slowly. I swear to God, it's actually impossible for me to draw a tree diagram. It is quite difficult, so I'll just quickly try my best. 1, 2, 3, 4, 5, 6. Okay. So over here we have 1. The problem 1 occurring, 2, 3, 4, 5, 6. And 1, 2, 3, 4, 5, 6. And then over here 1, 2, 3, 4, 5. And then 6. Oh, this takes a while, and normally the tree diagrams in the actual exam get really clumped up. But the point is, so everybody else has drawn a proper tree diagram, right? I literally don't have enough space and cannot do it on a drawing tablet. But I'll give you guys a question to use to try solving using your tree diagram. So what's the probability of me getting a 6 and then a 1? So can everybody calculate it and then type the answer to the Skype chat? Okay, that's one person. 0.02. All right. All right. Yeah. Okay. Cool. Yeah. So, so basically, for this, right, we want an answer that's more like Daksh's and less like Raja's, because we don't want to say 0.02. In probability, we rarely use decimal points unless we have to, right? So what Daksh did is he realized that the probability of a 6 occurring is 1 on 6, and then a probability of a 1 occurring is 1 on 6, and he just multiplied them together, right? So he ended up getting 1 over 6 times 1 over 6, which is 1 over 36, and that's the probability of a 6 and then a 1, right? Now let me make it a little bit harder. What is the probability of me getting even number on both rolls? So probability of even number, so an even number on both rolls. One over 4, 1 over 9, 1 over 4. Okay, so there's obviously two methods to calculate this, right? 1 over 12, all right? Let's try method 1, and let's see who ends up right. So method 1 is just summing up the total probabilities, right? So let's just sum up total probabilities. Okay, so obviously we need to get both even numbers. So 1 is out. We can't get a 1 on the first roll. We can only get a 2 on the first roll, a 4 on the first roll, or a 6 on the first roll, right? If we get a 2 on the first roll, then we need a 2 on the second roll, right? So over here, let's write down what they are. So that's 2, 2. We can get a 2, 2 plus a 2, 4, or plus, this is not 24, it's 2, 4, by the way. Or I should probably put dashes between them. Maybe that'll make 2, 2 plus 2, 4 plus 2, okay, Omi's just changing his answer, all right. Plus 4, 2 plus 4, 4 plus 4, 6 plus 6, 2 plus 6, 4 plus 6, 6, right? So you can see those are our total probabilities, and each of them have a 1 in 36 chance of occurring, right? So each of these probabilities has a 1 in 36 chance of occurring. So how many of these probabilities do we have? Because remember, it's a fair dice. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So what do we end up with? Can anybody tell me? Because I'm pretty sure, like, everybody got it wrong. Oh, is 9 on 36 1 on 4? Is it? Oh, yeah, it is too, huh? I'm a genius. Yeah, so it's 9 on 36 and it's 1 on 4. Yeah, I wrote I wrote 9 on 36 on my paper and I was like, what the hell is this? All right. Yeah. All right, cool. That's good. Now I'm going to give you guys one more hard problem. One last one. And this one's worth all the money. I guarantee if you get this problem at this stage, right? If you get this problem at this stage of like knowing probability with the knowledge that I've just taught you, you're guaranteed to like get top 5 for like core. Like if you can get this answer, right? So it is, what is the probability? What is the probability that at least one number in both roles, in either roles, is even? No, it's not. It's not. It's a really simple question. This one's super simple. It's not that like when you guys do core 4, this is a super simple question. But right now, this is like super difficult. So what is the probability that at least one number in either roles is even? If if you have no idea where to start, can you please type a 0? 3/4. Okay. Okay, so Daksh has 3/4. Does anybody else have an idea on what to do? Please type a 1 if you know what to do, and type a 0 if you have no idea where to start. I'll give you guys a minute. Alright, I think everybody's had an attempt. Okay, let's have a look at what actually just happened. So probability that at least one number in either roles is even. So before I start trying to solve this problem, we need to understand something called complementary events. Oh, okay, 27 on 36, 3/4. Alright, cool. Alright. So there's actually a really easy way to do it and a really hard way to do it, right? At least one number is even in either roles. You can just do the manual calculation, right? But that takes way too long. There's a shorter way to do it, and that is knowing the total probability. And what I mean by that is, Raja, if I summed up the probabilities of every single event occurring in the 2 dice rolls, what would I get? What would be my total probability? Do you know?
Say that one more time.
So if I summed up all the probabilities, like all the possible events in my 2 dice rolls, right? If I summed up every single possibility in this tree diagram, what would my total probability be?
36, like 1 on 30.
36 on 36, right?
Oh, 36 on 30.
Yeah, so it'd be 1?
Yeah.
Yeah, so 100%, right? Because if I considered every single event occurring, it's a 100% chance of every single event occurring, right? So if you think about it, the probability of at least one number, even in either roles, is the same thing as saying the total probability, 1, minus the probability of no even number occurring. And obviously, no even number occurring would be the same as as basically saying that there's just both odds, right? Both odd numbers, which is going to be the same probability as both even numbers. So that's 1 on 4, right? So we just have 1 minus 1 on 4, which is equal to 3 on 4. So whoever got 3 on 4, well done. I think Daksh got it like instantaneously. So what a god. Anyways, that is probably like the hardest question you guys have probably solved ever in high school. Yeah, probably, honestly. The good thing about this session in core is that it's a brand new start in terms of like, it's like Chem 3. Like, you don't need to be like a super genius to be able to like top and beat Renusha. Even though Renusha did top Chem 3, but that's only because he works insane. But like, you can get really, really high scores in core 4 if you just like practice. I mean, yeah, because it's like a completely different mindset. Anyways, so now there's one more law we need to introduce, and that's 2 more laws actually. But I'm not going to write down the definitions. That's for actual core 4. I'm just going to explain them really, really obviously. So that's called the multiplicative and additive laws, right? So multiplicative and additive laws. So there's only one way to explain this. Now let's say you're Rohan, right? And Rohan is the definition of budget. So you're really budget, right? And what's happening is that you need to go from home and you need to go all the way to school, right? Now, obviously, there's a bus station in the middle, right? Because Rohan's budget, so he doesn't catch a car because he realizes that his fuel economy is too high. So, his fuel economy is too low, so he needs to catch the bus, right? It saves him money. So what happens is there's a midpoint bus station, right? Now, from home, there are actually 3 buses that go to the bus station, right? Let's say. So one's the 6, the 4, and the something, the 57. And from the bus station to school, there's actually 4 buses, right? However, Rohan does have the option of just catching a car, right? That's the car. So let's figure out how many ways from home to school, right? So how many ways can Rohan possibly take from home to school? Even though we're more concerned about his budget issues, but we'll just like talk about how many ways he can go from home to school. So obviously, let's have a look here. So obviously you can go down this path, right? So let's say this is path number 1, 2, and 3, right? So if you go down path number 1, after that you have 4 choices. If you go down path number 2, after that you have 4 choices again. If you go down path number 3, you still have 4 choices. So in fact, you have 3 times 4, right? Total ways of getting from home to school. Because from home, there are 3 choices to the bus station. And then there are 4 more choices back to school, right? But there is the addition of that car ride that Rohan so regrets. So there are 13 ways in total of getting from home to school, right? Now let's have a look at what I actually did there. So notice that we start. So now let's analyze what we're doing. So notice we start here, right? We start at home, right? And every time we reach a midpoint, so bus station is a midpoint, right? Or a midpoint or a point in between the end. So the school is the end, right? The destination. So I'll call it the destination. It's probably easier. Okay, so school is the destination, right? So every time there's a midpoint and we have possible routes to reach our destination, we multiply. So multiply through that. However, if we have something that goes directly from the start to the end, to our destination, without going through any midpoints, we just add it, right? We add the car, but we multiply the possible possibilities to get to school from the bus station because we have to stop halfway in between, right? So over here, if we go back to our tree diagram, you'll notice that since our destination is 2 total coin tosses, right? It's 2 tosses. We have to multiply in between these because we haven't reached our destination from the start. right? Our destination is that final toss. So we have to multiply in between them. However, it said, what is the possibility of 2 heads and then a tails? And you can just add that remaining bit, right? Okay, well, not then a tails. Then it would be like in a separate coin toss a tails. But then a tails would just be multiplying it again by 0.5. But, yeah. So, let's summarize this. So, if when we are, I'll just quickly type this up because, oh, no, I can't type it up. So, when we are going between oops. So when we are going between 2 places, we multiply, right? So if we're going from our home to the bus station to school, we have to multiply, right? But if we go directly from home to our destination, then we just add. So that makes kind of sense, but we're gonna do a little bit of problems to make sure we all understand this. So before that, I'll quickly say steps to destination. So every time we take steps to our destination, we multiply. Every time we straight to destination, yeah. We add, right? So now let's move on, and I'll give you guys an example after just this little bit to make sure you guys understand what I mean by this. So we're going to introduce permutations and combinations. Okay, permutations and combinations. So the most basic question anybody ever asks in permutations and combinations, so we're going to be focusing on permutations right now, so is how many ways, so I'll just use like a nicer color, purple. How many ways to arrange 5 markers? How many ways to arrange 5 markers of all different colors, right? So let's say I had 5 markers. Now notice the keyword is arrange. So that means order matters. So what I mean by that is if I had 5 markers, red, green, blue, orange, purple, right? Then this is completely different to red, blue, green, orange, purple, right? These are different because the markers are arranged in a different way because we have green here and blue here. Right, so they're different. So my question is, what are the total amount of combinations? What are the total amount of permutations of these 5 markers? Does anybody know this, like instantaneously? Can anybody just look at it and tell me the answer? If you can you type it in the comment? Ooh, okay. Yeah, perfect. 5 factorial. Yeah, perfect. I wrote 60 as 5 factorial. So the reason that works, now let me explain why it's 5 factorial. So let's say we have our boxes, right? And we're going to say, these are my boxes. Like, let's say I have boxes. And I'm going to put markers into this. So I start off with 5 markers, right? Now, Daksh, if I wanted to put a marker into this box, how many choices of markers do I have?
You have 5.
Yeah, so I have 5. Now, notice that we haven't reached our destination. We're just starting. So, Raja, since we're starting here, what type of operation goes in between these boxes?
Multiplication.
Multiplication, right? So now, how many choices do I have left, Frank, in the second box to put?
We got 4.
Yeah, 4, and then again multiplication. So we have 3 and 2 and then 1, right? And this is equal to 120, like Daksh said. But since mathematicians can't always be bothered to write 5 times 4 times 3 times 2 times 1, especially if the question was, arrange 20 markers, right? Like nobody can write that. We denote this as 5 factorial. right? So, and 5 factorial means you just multiply all the way down to 1. So, I'll just quickly summarize factorials for you guys. So, a factorial, like n factorial, is starting from n and going down by 1 to 1 multiplying. So what I mean by that is 6 factorial. Frank, can you tell me what 6 factorial would be? Hello, Frank?
Hello?
Yeah, what would 6 factorial be?
Is that 720?
Yeah, but what would we how would we express it? Like,
Oh, just,
yeah. So 6 times
oh, it's 6 times 5
Time.
times 4.
times.
And it goes down to 1.
Yeah, perfect. So that's 6 factorial, right? So Raja, how would we show 7 factorial?
Sorry, did you ask what 7 factorial is?
How would we show it? Yeah.
7 times 6 times 5 times 4 times.
Yeah, perfect. Okay, cool. So now I'm gonna make it a slightly more tricky. Now, what is 7 times 6 factorial equal to?
7 factorial.
Perfect. So the reason that is because 7 times by 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. But we see that that is the exact same as this, right? So this is still 7 factorial. Whoops, 7 factorial. So now if you look at this, right, the general rule of that is n plus 1 times by n factorial is equal to n plus 1 factorial. That's the general rule of that how should I say this, of that operation, of that thing. Now, Daksh, let me ask you this. I want an answer without using your calculator. What is 7 factorial on 6 factorial?
Isn't that just equal to 7?
Perfect. Yeah, it is 7. So the reason is because 7 factorial is the same as saying 7 times 6 factorial on 6 factorial. These cancel, so you're left with 7. Right? Now, Raja, what is 7 factorial on 4 factorial? I don't need an answer. I just want you to simplify this for me.
So is that gonna be 3 factorial?
No. So what's happening here is 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1, right? But this right here is just 4 factorial, isn't it? So what's happening is this is just 7 times 6 times 5 times 4 factorial on 4 factorial. So we're just left with 7 times 6 times 5. Does that make sense, Raja? Hello?
Yeah, it does.
That does make sense? Okay, cool. So, Raja, can you tell me what is 8 factorial on 3 factorial going to equal?
Is that gonna be 8 times 7 times 6 times 5 times 4 times, yeah, and
Yeah, perfect, times 4. Good. That's perfect. So, another way to express that is basically saying n plus 1 factorial on n factorial is equal to n plus 1 and etc. Right? That works for everything. So just these simple operations, right, help a lot in solving these factorial problems. Now, one of the other things that I'm going to say, since we're talking about arranging here, factorials is purely to do with arrangements. Yes, it pops up in other places, but it's got all to do with arrangements. So, Daksh, let me ask you a hard question. Why is 0 factorial 1? If I told you that everything is based purely on arrangements.
Just because there's only one way you can arrange 0 things.
Perfect, yes. Because there's only one way to arrange 0 things. And that is by not arranging it. So that's not arranging, right? So you just not arrange it. Cool. So that's why 0 factorial is equal to 1. Some people just say that's a, what do you call it? Like an axiom, but it's not. There's actually a good reason why it's equal to 1, right? There's No, there's only one way to arrange 0 things, right? Now, what if I said, let's say, what if I said I can make this more complicated? So what if I said that how many ways to arrange 4 objects from 8 objects? Raja, do you have an idea?
Yeah, it's gonna be one of the operations that we just did.
Close, yes, but there's another way to do it. Every time you're in doubt, just do the box method, right? So there's 4 objects, so we have 4 boxes, right? Now, how many choices of markers or objects do I have in the first one, Raja? In the first box. So I have 8 objects in total.
Could be 8.
Yeah, I have 8. And then how many do I have?
7.
And then how many?
6.
And then?
5.
And what's the operation between them?
Multiplication.
Perfect. So that is how many ways to arrange 4 objects from 8. This is also denoted as 8p4. So out of the 8 objects, we have to permute 4 of them. Okay? That's how it's donated, right? And that's equal to 1,680. That's also in your calculator, P and C. So P is permute, which is the arranging, where order matters. All right, and we'll explain combinations in a bit. But let's try to generalize. Let's generalize this, right? Okay, Daksh, if I said it's NPR, what would my formula look like? What would my general formula look like?
Would you have n factorial divided by r factorial?
Close. So let's say, Daksh, because I just used let's say I had 8 objects, and I wanted to arrange 5 of them. What would I multiply? So I'd have 5 boxes, right?
Yeah. Oh, okay. So would you have like 8 divided by 8 minus 5 factorial?
Perfect, right? Yeah. So in the general form, what would it look like?
So it'd be n factorial divided by n minus r factorial.
Yep. So it's n factorial on n minus r factorial, right? That's our general form of permutations. No, Raja, it's not the same, because you can see over here, that's actually what we're doing. This is actually what we're doing, right? But you can simplify it. So for example, if I had 8p6, right, that's just the same thing as saying 8 factorial on 2 factorial, which is equal to 8 times 7 times 6 times 5 times 4 times 3. Even though that's not very simplified, it's still close enough, right? Now, Raja, let me ask you, what would the condition on R have to be? So if you had to give R a maximum and minimum value, what would it be?
Does it have to be less than n?
So yes, it has to be less than or equal to n. Because remember, 0 factorial is 1, right? So if R is equal to n, this is n minus n, right? And that's 0 factorial, which is 1. So yes, it has to be less than or equal to n. Yep.
Do you mean in terms of like reals and stuff, or is that not?
Oh, well, obviously R has to be a number, right? We can't have 3.4 of an object, hence why we never have 3.4 factorial.
Yeah.
Yeah. So what do you reckon the smallest value of R could be? Remember, that's the amount of objects we choose to arrange. So n is the total objects, right? And R is the amount of objects we choose to arrange. What do you reckon the smallest amount of objects I could choose to arrange is?
Can it just be any positive integer?
No, so it has to be 0, right? Because I can arrange 0 objects, right? So R is anywhere between 0 and n. For example, if we look up here, how many ways to arrange 4 objects, right? I could just say how many ways to arrange 0 objects, right, Raja? Does that make sense? I could say how many ways to arrange 0 objects.
Yeah.
Right? And I could say, and the maximum I could say is how many ways to arrange 8. Why couldn't I say 9, Raja? Because you have a total of?
Because you only have a total of 8 objects.
Yeah, so you have a total of 8 objects, so you can't arrange 9, right? And you can't get negative objects, but you can have anything greater than 0 or equal to 0, but you can't have anything more than 8. Does that make sense?
Yeah, that makes sense.
So That's where our range of R is in between, right? So let's say, Raja, I wanted to figure out how many ways to arrange 0 objects from 8 objects. How many ways would there be? So that's 8p0. How many ways is that?
Hold on, let me think. So you're saying that would be
So just use the formula.
factorial on 0 factorial.
8 factorial on 8 minus 0 factorial.
Also 8 minus 0
So
factorial.
that's 1, right?
Yeah.
Or another way to think about it is you just don't arrange the object. That's the one way to arrange them. Right? There's only one way
Yeah.
to arrange them. So, now that we understand permutations to a basic extent, we don't need to know very hardcore permutations. Let's talk about combinations, right? Combinations. So combinations is basically like choose, right? It's choose. So we have to choose what we're doing. So, for example, let's say we said I have 8 objects and I choose 4, right? So in this, order doesn't matter. And I'll explain why. Order doesn't matter. For example, from my 8 colored markers, I could pick the 4 objects, right? I could pick the 4 markers red, green, blue, orange, or red, orange, green, blue, or red, blue, orange, green, right? They all don't matter because at the end of the day, I still picked up those same 4 markers, right? However, if I picked up red, purple, blue, orange, that's different. These two are different because I picked up a different marker, right? So I picked up a different marker. I picked up a purple and then a green, right? There's a difference. However, these all are the same because I picked up the same markers. So you can see how order doesn't matter, right? So these are combinations. So let's try combinations. Let's try a really simple example. How many ways to choose 2 objects from 3 objects? Who knows the answer? Who can just type it in there right now instantaneously? Does anybody know the answer? If you don't, can you type a 0? Okay, so one person knows an answer. The answer. Yeah, so 3 is the total ways of arranging them. Okay, so let's have a look at how I did this, or how Daksh solved it, and how anybody else does it. So the first thing is first, right? Notice it's choose, not arrange. The first thing is first, let's find out how many ways to arrange 2 objects from 3 objects. From 3 objects, 3p2, can, Raja, what's 3p2 equal to? That's 3 factorial on?
Three minus 2
Yeah,
factorial.
so that's
Sorry,
1 factorial.
3 minus 2 factorial.
Yeah, so
two, one.
that's 6 factorial. I mean, sorry, not 6 factorial, that's 6, right? 3 times 2
Yeah.
times 1. Right, cool.
Yeah.
So that's 6, right? Now there's 6 ways to arrange those objects. But now, Frank, for example, I wanted to get rid of the arrangements. So for example, I could pick my 2 markers and they could be red and green. Or they could be green and red. If I wanted to get rid of my arrangements, what would I have to divide by?
What do you mean?
So I have 2 arrangements, right? So let's say I had 3 markers. Let's say I had red, green, blue, right?
Mm-hmm.
And I picked red and then green, right? That's how I chose. That's how I arranged them, right?
Mm-hmm.
But so remember when we're arranging, this is different to this, right? Green and then red. So what do I have to divide by to make sure that they're the same thing? They're counted as one thing. Do you know?
Wouldn't it just be one of the markers, or no idea,
No
sorry.
clue. Daksh, do you know what we would have to divide by to get rid of the possible arrangements?
Yeah, since we are choosing from 2 objects, you would also divide by 2 factorial.
Perfect. So we have to take our total amount of total amount of permutations, 6, and then we have to divide by the amount of ways you can arrange 2 objects, which is 2 factorial. So we end up with 3, right? So let's try another one. Let's add 5 markers. and I needed to choose 3. Omi, how many ways can I choose 3 from 5 markers? Omi? Hello?
Wait 1 sec, can I think about this?
Yeah, sure.
Uh, is it 10?
N
10.
10. Okay.
Yeah.
Let's have a look at let's have a look at what Omi thinks is the correct answer. So, it is the correct answer, by the way. But like, let's have a look at what he did. So, we have 5 markers, right? So the way to arrange 3 of them is 5p3, right? And 5p3 is 60, right? 60. 5p3 is 60. So that's 5 times 4 times 3, right? I think. Yeah, it is. 5 times 4 times 3. That's 60, right? Now, remember, since we're choosing 3, the order of them don't matter. So it could be red, green, blue, or red, blue, green, right? Or red, or blue, green, red, or blah, 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 right? And so forth. So this order doesn't matter. Now, over here we can see we have 3 markers, but the order doesn't matter. So out of the 60 total arrangements, we have to get rid of the ones where they're the same, right? Because we're picking the same markers. It doesn't matter if they're red, green, or blue, blue, green, or red, right? If I put my hand into a bag and I get a blue, red, and a green ball, it doesn't matter if I got the blue first, the red second, and the green third. I just needed the blue, red, and the green, right? So we need to get rid of these total arrangements. How many ways are there to arrange 3 objects? There's 3 factorial different ways, which is 6, right? So that's just saying 5p3 on 3 factorial, which is equal to 60 on 6, which is equal to 10. So yes, there's 10 ways to choose 3 markers from 5. Now, Raja, if I had n objects and I had to choose r of them, what would my general formula look like? Do you have any idea? Hello, Raja?
Hold on, can you?
Yeah.
Yeah, sorry. I am muted. Hold on, can I have a second to think about it?
Yeah, sure.
Would it be
Oh, sorry.
like NPR on R factorial?
N, perfect. Good. So it's NPR on R factorial, right? Which is also the same as saying, if we know what NPR is, we know it's N factorial on N minus R factorial divided by R factorial. So that's the same thing as saying N factorial on N minus R factorial R factorial. So N choose R is equal to N factorial on N minus R factorial R factorial. That right there, oops, is our general formula. Okay? So, now that we understand this, we're going to learn this one stupid thing that they refuse to teach in Core 4, but you need to know because it's like so important towards like your understanding. And then we're going to revise induction by using our knowledge of what we just learned. So we're going to learn binomial expansion. So, who here has heard and can draw a Pascal's triangle? Can you type a 1 if you can draw a Pascal's triangle? Wait, Omi, you can't draw a Pascal's triangle?
I mean, like, I can, but like I get stuck past like 1, 5, 10, 5, 1.
Whoa, alright. Frank, can you draw a Pascal's triangle?
Yeah, not really confidently.
Alright. So let's just have a little revision on Pascal's triangle. I was kind of hoping we didn't have to, but well, let's just do it anyways. Okay, Pascal's triangle, right? So, Basically, Pascal's triangle is to help us with the expansion coefficients, right? So what I mean by that is if I had a plus b to the power of 0, I would get 1, right? But if I had a plus b to the power of 1, I'd get a plus b. So over here, our coefficients are 1 and 1 for b and a respectively, right? And over here, a plus b squared is equal to a squared plus 2ab plus b squared. So our coefficients here are 1, 2, and then 1 again, right? So Pascal's triangle is to use to help us figure out those coefficients. So the power of 0, so over here n, we're gonna do this as a general thing. So I'll just say a plus b to the power of n. So when n is equal to 0, it's just 1, right? Our coefficient is just 1. When n is equal to 1, our coefficient is 1 and then 1, all right? And then when our coefficient is n is equal to 2, I'll just write over here. We have 1, 1, and then 2, right? So basically, the way that we draw this Pascal's triangle is just we keep writing 1s down the edge. So 1s down the edge. And then we fill in the gaps by adding. So over here, we just added these two numbers to get to this number. So again, 1s down the edge, and then we have to add, right? So we add these two numbers, we get 3, and we add these two numbers, we get 3. So, Omi, can you fill in the next line for me?
Sure. So it'd be 1,
Yep.
4, 6, 4, 1.
Perfect. Now, Frank, can you fill in the next line after that?
Yep.
Yep.
So 1, 5, 10, 10, 5, 1.
Perfect. Daksh, can you fill in the next line?
Yeah, the next line would be 1, 6, 15, 20, 15, 6, and then 1.
Perfect. And notice this is n is equal to 3, n is equal to 4, n is equal to 5, n is equal to 6. N is equal to 7. Raja, can you fill in the last line? Just making sure everybody can do it. Yeah?
Yeah, so it's going to be 1, 7, 21, 35, 35, 21, 7, 1.
Perfect. Good, good, good. So, that's great. So everybody right now, if you type a 1 if you guys are confident with drawing a Pascal's triangle now. All right, cool. So everybody's confident drawing a Pascal's triangle. I'm glad. All right. So now let's just quickly, before I do binomial expansion, I guess we're just going to have to quickly revise what a Pascal's triangle is used for, right? So over here, we have a plus b to the power of 7, right? Let's just do n is equal to 6 first. So let's say a plus b to the power of 6. Now the way that we figure out what this is equal to is we use Pascal's triangle. In specific, we use our line of 6, right? So first thing you need to know is that the powers of a go down. So a go down and b go up, starting from the left-hand side. So starting from the left-hand side to the right-hand side, a goes down, b goes up. So what I mean by that is the maximum power here is 6. So a to the 6, b to the 0. Then we have plus a to the 5, b to the 1, plus a to the 4, b to the 2, plus a to the 3, b to the 3, plus a to the 2, b to the 4, plus a to the 1, b to the 5, plus b to the a to the 0, b to the 6. Hold on, give me a second. A to the 0, b to the 6. Now, sorry, I'm going over this stuff because I don't have enough space. I'll probably just do it later down there. But now let's insert our coefficients, right? Let's insert our coefficients. So I'll quickly go down here and rewrite that. Even it's probably not going to take me that long. Sorry about that. A to the 6, b to the 0, plus a to the 5, b to the 1, plus a to the 4, b squared. Cool. So over here, we have this, right? So that's how we draw our powers out, right? So notice that the sum of these powers is always going to be 6, right? The sum of these powers still remains 6, but a goes down by 1 and b goes up by 1. So now let's insert our coefficients, right? So over here, and n is equal to 6, our first coefficient is 1. So we put a 1 here. Our next coefficient is 6. We put a 6 here. Our next one is 15. We put a 15 here. Our next one is 20. Then our next one is 15. Then our next one is 6. And then 1. So a plus b to the 6 is equal to a to the 6 plus 6a5b plus 15a4b squared plus 20a cubed b cubed plus 15a squared b to the 4 plus 6ab to the 5 plus b to the 6. Does that make sense? So I'll quickly just give you guys one to do. So can everybody please do a plus b to the 9? Oh, that's way too much. Let's just do 5. Can everybody? No, let's just do 7. Can everybody do a plus b to the 7? I'll quickly show you guys the 7th line of the Pascal's triangle. So one type of 1 when you're done. Frank, have you almost finished? Or are you stuck? Oh, you're finished. Okay, cool. So, Frank, can you tell me the first 3 coefficients? The first three, how should I say this? Yeah.
Yeah,
Powers.
1, 7,
Yeah.
21.
So we have, what do we have?
1, 7, and 21
So-
for that one.
No, like, can you
So a to the
Yeah.
power of 7
plus?
plus 7 a to the power of 6 times b.
Yeah.
Plus 21 a to the power of 5 b to the power of 2.
Okay, now, Raja, can you tell me the next 3? Next 2, actually, and then Umi can tell me the last bit.
Yeah, just give me a second. Where are we up to? Okay, so 35a to the 4b to the 3
Yep.
plus 35 to the 3b to the 4.
Mm-hmm.
Do you want another one?
No,
Or is
no,
that
no,
it?
Umi. Umi, can you tell me the last 3?
21 a to the 2 b to the 5.
Mhm.
7 a to the a and then b to the 6 and then plus b to the 7.
Perfect. So everybody gets how to do expansion now? Yes? So what we're going to do now is we're going to take our Pascal's triangle and now we're going to do it in terms of combinations. This is going to be crazy. So 1, I'll quickly just write down my little Pascal's triangle, which is going to be much larger now. 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. I need to go to 5. 1, 5, 10, 10, 5, 1. Cool. So we have our Pascal's triangle over here, right? Now, obviously, over here is n is equal to 0. I'll quickly put that in red. Actually, I'll put that in purple. N is equal to 1. Okay. So basically, the way that we think about it, right, is that we think about n as our amount of objects. So n is our objects, okay? N is our objects, and I'm not going to explain how this works. I'm just going to explain that and to show you that it works. And then when you do core 4, you'll understand why it works. But for now, n is our amount of objects, right? So over here we start off with 0 objects. So 0 choose. Daksh, what's the only possible value of r we can have?
0.
Yeah. So what's the answer?
Is it just 1?
Yeah. So you can see over here that it's just 1, right? Now, for one object, Raja, what are the only 2 ways we can? What are the only 2 values of r we can have for one object? So, do you know?
1 and 1.
1 and 1. Are you sure? So when we have one object, there's 2 ways of picking objects from one object. There's you pick no object.
Nothing or like
Yeah,
1.
perfect. And what are they both equal to?
1 and
1
1.
and 1. Perfect. So you can see that they're 1 and 1 respectively. So that's 1 choose 0, 1 choose 1, right? Now, for 2 objects, let's just try doing this for 2 objects. Hopefully this works. Whoops, I'll just actually bring that back. So for 2 objects, right, we have 2 choose 0. And Frank, what's 2 choose 0?
Is it just one?
Yep. And 2 choose 1. So from 2 objects, we choose 1. Omi, what would 2 choose 1 be?
Would it be 2?
Yeah, so you can see the similarities forming, right? And 2 choose 2 is 1 again, right? Now, by this, right, you can actually generalize this formula. So, for example, again, like what Omi said, if you had 5 objects and you chose 3 of them, you would get 10. If you remember, we did that question, right? So, you can actually do, what do you call it? You can actually make a general formula. So, Daksh, a plus b to the power of n, could you give me a general formula for what it would look like?
It would be like a to the power of n
Yeah.
plus like some coefficient a to the power of n minus 1 b to the power of 1.
Oh, okay.
Plus.
So over here, obviously, remember we have to consider our coefficients, right? So
Yeah.
what we have to do is we have to start with n choose 0 because we have no objects in the first line, right? A to the n,
Okay.
b to the 0, plus n choose 1, a to the n minus 1, b to the 1.
Oh,
Plus
okay,
n
okay.
choose 2, a to the n minus 2, b squared, plus, plus n choose n minus 1, a, b to the n minus 1, plus n choose n, b to the n, right? Does that make
Yeah.
sense?
Yeah,
So
that makes a
you
lot
can
of
see
sense.
that's the general formula for expanding anything. So actually you can figure out the coefficient of anything on any power. So what I mean by that is, for example, I had a plus b to the power of 37. Yes? Now if I asked you to tell me what the 16th term in that sequence, what would its coefficient be? Could you guys tell me? So I'll give you guys like 30 seconds to figure this out. So can you guys tell me the coefficient of the 16th term? But what I mean by coefficient is like if we did a to the 5, the coefficient over here is 21, right? So like stuff like that. A to the 7, sorry. A plus b to the 7. So can you guys tell me the coefficient of the 16th term? Notice this is the first term, second term, third term, fourth term, fifth term, sixth term. So can you guys tell me the coefficient of the 16th term? Type a 1 when you're done. Ooh, okay. We got one person done already. I'll wait for like a couple more. Type a 0 if you don't know how to do it. Or type a 0 if you think you're taking way too long. Okay. So, Daksh, what did you get as your answer?
I'm not sure if I'm right. It's a pretty big number, 1.287577464 times 10 to the 10.
Okay. And Frank, what did you get?
I didn't get numerical, but I think I don't know if I got the basic gist. Is it just 37 factorial divided by 15 factorial?
Okay, that's your answer. Umi, do you have an answer?
I got 37 choose 15, whatever that equals to.
37 choose 15. Okay, cool.
Yeah, that was what I got as
All
well.
right, cool. Let's have a look at 37 minus 16 factorial. Okay, let's just see what happens, okay? So, over here as you can see, n choose 0 gives us our first term, right? N choose 0 gives us our first term. So n choose 1 gives us our second term, right? So if you want to figure out our 16th term, we have to do 37 choose 15, right? So over here what we get is 37 factorial on 37 minus 15 factorial 15 factorial, right? So what we end up getting is, I'll just quickly tell you guys. Whoops, I'm actually being weird. 37. So we get is a really, really big number. And you can see why this is so powerful. It's 93641999760, right? So that's the number we end up getting, which is huge, right? But you can see how that makes sense because we're actually looking at our 15th term. So generally, if we had a plus b to the power of n and we wanted to find our rth term, we would do n choose r minus 1. Or no, I'll say kth term because k would make more sense. K minus 1. Okay, and that's our general formula for finding our kth term, right? Okay, good. So does everybody get binomial expansion? Type of 1 if you understand binomial expansion and you feel like you can expand anything. Alright, so Frank and Raja. Raja, do you have a problem with binomial expansion? Oh no, okay, you get it. Frank, are you still a little bit confused? Alright, no, he's not confused either. Okay, apparently nobody's confused. Okay, so the last little bit left is induction. So first of all, we need to do series and sequences, right? Series and sequences. Okay. Now the reason I'm going to show you why this is so important, series and sequences, I'm going to give you guys a core 4 problem. Simple core 4 problem, okay? That you guys have enough probability to solve. Okay. Let's say me and Daksh, love playing heads and tails, right? Coin tossing. We love coin tossing. So I challenge Daksh. Actually, Daksh challenges me because he's more cocky. No, I'm kidding. I'm more cocky. But let's say he was more cocky. To a coin toss game, right? But he says I can toss first, right? And we toss till someone gets a heads, right? So 2 people play a game. So person A and B toss till first person gets heads. Okay, so person A and B toss the coin till first person gets heads. And whoever gets heads wins, right? They win. So what is the probability of me winning, person A winning, me winning, if I go first? Alright, bro. Oh yeah, funny. So does anybody immediately tell me the answer just by typing it in? Because I would be genuinely shocked if someone could tell me what the answer is right now. If you guys have no idea how to solve this, can you type a 0? Okay. 0, 0, 0. Great. So I'm going to introduce series and sequences after I show you this problem because I want to show you the importance of series and sequences. Okay. So let's say me and Daksh toss a coin, right? So let's say I go first, right? So let's draw a tree diagram because tree diagrams are useful. So we have heads. If I get a heads, I win. If I get a tails, then Daksh tosses. Notice Daksh tosses, right? And if Daksh tosses, he gets a heads and he loses. I lose, right? But if he gets a tails, then I toss again. And if I get a heads, I win. If I get a tails, Daksh tosses again. And if Daksh tosses a heads, I lose. If Daksh tosses a tails, then I toss. I get a heads, I win. If I get a tails, Daksh tosses. Daksh gets a heads, I lose. Ahmed. Then I toss a tails. Tosses a tails, and I toss. Right? If I toss and I get a heads, then I win. If I toss a tail, so forth, right? So this goes on and on and on. So this is So can anybody tell me what type of series this is? What type of series would we need to solve this problem? Just by looking, just by infinite, exactly. Because me and Dux could, there is a possibility, a small one, but a possibility that me and Dux could toss infinite tails, right? So we would have to consider an infinite series. Now, how this works. Again, remember in our probability diagram, we have to write 0.5 everywhere because it's a coin toss, right? So guys, this is, by the way, this is a pretty decently difficult core problem. This is not an easy problem by any means. So if you guys are struggling with this one, don't feel bad about yourself because this is the type of problem you do halfway through core 4. But I want to show it to you because I think you guys have the understanding to understand it, but just not to be able to approach it. So what happens is, let's consider me winning. So probability of me winning, going first, is equal to, so obviously if I get the first toss, I get a heads, it's a half, right? Then the next time I get a heads is if I went 0.5 times 0.5 times 0.5. Remember, we have our start and then we have our destination. So we have to do multiplication between them. So it's a half times a half times a half, right? Plus, now the next time I win is over here. So that's 0.5 times 0.5 times 0.5 times 0.5 times 0.5. That's a half times a half times a half times a half times a half. So there's 5 halves there, right? So in other words, that's a half plus a half to the power of 3 plus a half to the power of 5. Now, if you remember our infinity formula, the sum to infinity is equal to a over 1 minus r. A is our first term, and r is our common ratio. So Dux, what's our common ratio in this case?
Is the common ratio just 1 on
1 on 4?
Yeah, so 1 on
perfect.
2 squared. Yeah.
So the common ratio in this case is equal to 1 on a half squared, or 1 on 4, right? Perfect. So, and then what's our first term, Frank?
It's just the half.
Perfect. So what we end up getting is S infinity is equal to a half on 1 minus a quarter, which is equal to a half on 3 over 4, which is equal to 2 over 3. So 2/3. So I actually have a 66.67% chance of winning if, what do you call it? If I toss first. Does that make sense? So notice, if you're going to challenge someone to a coin toss game like that with money on it, just always go first. You have a 2 in 3 chance of winning. Right? So can you guys see why series and sequences are super important? So let's do some series and sequences. So let's talk about the 3 types of sequences and series we have. So obviously sequences and series, same thing. Series, there's 3 types. Omi, what are the 3 types of series that we've learned in Core 1?
Arithmetic, geometric, and infinite geometric.
No. So we have arithmetic progression, geometric progression, and arithmetico-geometric progression. Okay? The infinite series is part of geometric progression, right, Umi? So it's the same series, although it's infinite. There are 3 series we've learned, 3 different types of series. We need different formulas for this series and this series and this series. However, this formula is actually just a simplified version of the geometric progression formula, and I'll derive it for you today. So if you guys, I debated on whether I should derive these formulas or not. Guys, if you want me to derive all 3 of the formulas, apart from the arithmetic or geometric ones, the arithmetic geometric progression ones, the really, really hard ones, can you guys type a 1 if you want me to derive the formulas? You don't need to know how to derive the formulas, but the techniques that you use to derive the formulas will help you a lot. Yeah, alright, so we derived them? Okay. So, arithmetic progression. Who remembers how an arithmetic progression works? Where do we start? Does anybody know? Can you just open your mic and say it? Or just type it in the chat? Does anybody know what we start with? A general arithmetic series. What would it start with? Yeah, perfect. It would start with A. And then we would add our next term, which over here is d. Now remember, a over here is again first term, and then d is common ratio, or common difference, sorry. And Dux, do you know why it's called a common difference?
Because the difference stays the same throughout.
Yeah. So if you take any two terms, any two consecutive terms in the series, and subtract them, you will get d. So the next one is a plus 2d, the next one is a plus 3d, all the way to a plus n minus 1d. Now, Raja, how many terms in this sequence, in this series, sorry? How many terms are there?
Is it n number of terms?
Yes, there's n number of terms. So there's n terms. Okay, perfect. So what I'm going to do for now is I'm just going to call this S, right? S. Now, the first thing what we're going to do is I'm going to rewrite S, but I'm going to rewrite it in a different way, okay? And I'm just going to move it a little bit to the side so you guys can understand what I'm about to do. S is equal to a plus n minus 1 d plus a plus n minus 2 d plus a plus n minus 3 d plus a plus n minus 4 d plus a, right? So what I'm doing is I'm writing this completely backwards. This is backwards. Okay? I'm writing the whole series just backwards. It's the same exact series because they're both S, remember? So I'm just writing it completely backwards. Can anybody tell me what this technique is called? Just type it in the chat if you know. Ooh, okay. So nobody's heard of the... Wow. No, this is called reverse addition. Okay? And it's not his technique, it's some Indian tutor's technique online. It's called reverse addition. Okay? And so over here, what we're going to call it, we're going to call this 1, and we're going to call this one 2. So what I'm going to do, okay, is... Can anybody tell me what I'm going to do? I'm going to end up doing? Or no, not really. Does anybody know what I'm about to do? Yeah, we're going to add them. We're going to take 1, and then we're going to add to 2. Okay? So on the left-hand side, I get 2s is equal to 2a plus n minus 1d. N minus 1d. Plus, over here, again, we get, so over here, this is 2a plus n minus 1d. All of these is 2a plus n minus 1d. Right? Alright. Now, how many of these 2a plus n minus 1d's do we have, Dux?
How many of them do
Yeah,
you have?
how
Do we
many
just
of
have
these do we have?
2? Like one at the beginning, one at the end?
No. They're all 2a plus n minus 1d's. So how many of these
Oh,
terms?
so do we just have n?
N of these, right? So we have n
Yeah.
times 2a plus n minus 1d, right? And that's equal to 2s. So s, the sum is equal to n over 2, 2a plus n minus 1d. Type 1 if you understand how I just did that. Alright. Omi, are you stuck on this or do you get it? Alright, cool. Okay. Now, there's another way to simplify it. What is the... Okay, if I said to you, right, the nth term, un, the nth term, remember this is the nth term, if you guys remember your little terminology, what is the nth term equal to in an arithmetic progression? Dux, do you remember?
Wasn't it like
It's right
the
here.
beginning term plus like n minus 1 times d?
Yeah,
Yeah,
perfect.
so the beginning term plus n
Yeah.
minus 1 times
It's
d.
a plus n minus 1 d, right? So over here, if you think about it, right, this is n over 2, 2a, which I'm going to make it a plus n minus 1 d. And this right here is our last term, un. So it's equal to n over 2, a plus un, right? So those are our two formulas. That's formula number 1, and that's formula number 2. So that's the first term plus last term formula, and that's just the other one where you don't have the last term. Does that make sense? Type a 1 if that made that made sense, kind of. Cool. Right. Great. Frank, did that make sense, or are you a little bit confused? Okay, cool. Now, let's do the geometric progression. Okay. Geometric progression has the most powerful technique. Notice this is the same technique used to solve all arithmetic or geometric progressions, okay? So this is the same technique to derive the formula as you use to solve any arithmetic or geometric series. And we're going to go through one. The reason that we're going to go through one is because in options 5A, you need it again, okay? So we need arithmetic or geometric, that's why. And they don't teach you arithmetic or geometric. They just never, they refuse to teach it to you. So I'll just quickly, yeah, cool. So let's do this. Hold on. Okay. Whoa, that's crazy. Dude, this is weird, man. Okay, anyways. So, geometric series. Can anybody tell me what it looks like? The general geometric series? Frank, can you tell me how it would start?
It's A again.
Yep.
It wasn't the formula like AR to the power of n minus 1 or something?
Yeah, close. So basically, we have A as our first, again, right? And then we have R and Raja, what is R?
Common ratio.
Common ratio. Perfect. So it's common ratio. And Raja, why is it called the common ratio?
Because every consecutive term has a common ratio.
Because if you take any two consecutive terms and divide them, your answer will always be R, right? So over here we get AR squared plus AR cubed plus AR to the n minus 1, right? So again, there's n terms here. So what I'm going to do is I'm going to call this S, right? S is equal to that, right? And what I'm going to do is I'm going to take the same S, but I'm going to multiply an R on both sides. So I'm going to get AR plus AR squared plus AR cubed plus AR to the 4 plus all the way to AR to the n. Not n minus 1, because the last term gets multiplied by R, makes it AR to the n. So now let me write this. S is equal to A plus AR plus AR squared plus AR to the 4 plus all the way to AR to the n minus 1. And RS is equal to AR plus AR squared. Notice this gap is on purpose, by the way. This gap is completely on purpose. AR squared plus AR cubed, AR to, I missed cubed, sorry. That's cubed. AR cubed plus all the way plus AR to, what am I doing? Okay. AR to the n minus 1 plus AR to the n. Now, I'm going to take this as equation 1, and I'm going to take this as equation 2. And now what I'm going to do, I'm going to subtract them. Okay? So over here, we get S minus RS is equal to, now notice this cancels with this cancels with this cancels with this, that cancels with that. So we're just left with A minus AR to the n. Right? And over here, I can factor out the S, I get 1 minus R. And I factor out the A over here, I get 1 minus R to the n. So I get over here, S is equal to A 1 minus R to the n on 1 minus R. Does that make sense? Please type a 1 if that makes sense. Cool, so everybody gets that. Hope, yep. Wait, alright, cool. Alright, cool, everybody gets that. Now let's think about an infinite series. Now, S infinity, let's derive this formula from this. Now, Dux, there's a condition on R for the infinite series. Can you tell me what the condition on R is for the infinite series? There's a range R has to be in.
Does R have to be like under 1?
Yes, the absolute value of R has to be less than 1, right? So basically R is a fraction, is what it's saying, right? So, if you think about it, S infinity is when the number of terms approaches infinity. Yes? Now, Dux, if I told you any fraction, A on B, to the power of infinity, and such that A on B is less than 1, any fraction to the power of infinity, what is it going to approach, Dux? Do you know?
0?
Yeah, so any fraction is going to approach 0, right? So we get S infinity, this becomes 0 for S infinity. So we get A on 1 minus r. And that's where you get your S infinity formula. There's a type of 1 if you understand that. Frank, do you get that? Yeah, cool. All right. So everybody's got that. So now that we understand the formulas, we must remember them and must understand where to use all of them, okay? And how to use them all. So that's just a quick revision. If you guys need more practice on these formulas, then you can DM me after the shoot for any more practice on anything that we've covered today, because I have a lot of content on this stuff. Anyways, so before we end this, we're going to do two more things. We're going to do an induction just to have a quick reminder. And we're also going to do one last arithmetic or geometric progression. So we're going to do an AGP, an arithmetic geometric progression. So what that means is it's both arithmetic and geometric. So type of 1 if you've done one of these problems before, yourself. Alright, so everybody's done one. Who can do one right now? Was it in the Core 1 test? Yeah, I don't think it was. I don't think it wasn't. Yeah, so let's have a look. 1x plus 2x squared plus 3x cubed plus all the way to infinity. Can everybody find S infinity for me? I'll give you guys a minute to solve it. Because if this S infinity is a lot easier than the other one. Or actually, I'll just ask you to find Sn, not S infinity. Sn is easier, sure. Oh, longer, takes a little while. Type of 1 when you're done with Sn. Alright, since we don't have much time, I just waited till the first person did it. So let's just do it, and let's just see how far everybody gets. So, first thing is first, what we do, so this is obviously going to go till n, obviously. So this is just like nx to the n, right? If we were to give it the nth term. So, what we're going to do is we're going to have, we're going to call this s, n, as is equal to x plus 2x squared plus 3x cubed plus... And by the way, this gets really messy if you finished it, right? It gets really messy towards the end. So what we're going to do is we're going to multiply everything by x. We get x Sn. This is equal to x squared plus 2x cubed plus all the way to nx to the n plus nx to the n plus 1, right? And we subtract these two equations, so we get Sn minus x Sn. This is equal to this, sorry. Yeah, so, sorry, yeah. Yeah. So when we subtract this, we get x plus x squared plus x cubed plus plus, so this is n minus 1 x plus x to the n plus x to the n plus 1. Right? And then using our simple geometric summing formulas, we know that this is just x1 minus x to the n plus 1 on 1 minus x, and that's equal to Sn on 1 minus x, and Sn is equal to x1 minus x to the n plus 1 on 1 minus x squared. So can everybody, wait, sorry, no, I made a little mistake. This is x to the n minus x to the n plus 1. So type a 1 if you end up getting this answer. Who ended up getting this answer? Did you even do it? Can you even see the screen? I don't think you can see the screen, dog. Oh, you put an n plus 1 somewhere. Oh, it's alright. Yeah, the process was the same. It's all about the process. It doesn't matter too much about this, and I had to kind of rush through it due to the lack of time. But the last thing we're going to do is an induction problem. Induction problem. Okay. Alright. There you go. Ranusha, if you have cost, you can join that. The last thing we're going to do is an induction problem. So the induction problem that we're going to do is we're going to show that a plus b to the n is equal to a to the n plus n choose 1, a to the n minus 1 b plus n choose 2, a to the n minus 2 b squared. By the way, this is an options 4 induction problem. Very popular induction problem. It's actually an options 1 induction problem too. It depends on how the teachers are feeling. So we're just going to quickly remember how to do this. So I'm going to walk you guys through this induction problem because I don't think we have enough time for you guys to try it, and I think it's very difficult too. So I think I gave Ranusha this and it took him like half an hour, dog. So I think it was in options 1 though. So Dux, can you tell me the first step to solving this problem?
Yeah, so you just assign n any arbitrary value, so like n is equal to 1, and then show it's true for that.
So for example, obviously for expansion, we're only going to assume that it's true for n is greater or equal to 0, right? So we have to show true n is equal to 0. So we get a, so on the, yeah, oh god, here we go. Ranusha, shush. It's equal to 1. And our right hand, oh god, and our right hand side is also equal to 1 because that becomes a to the 0 and the rest of them become 0, right? So we can see that it's true for n is equal to 0. All right. Now over here, let's Raja, what's the second step to induction?
Assume true for n equals k.
Assume true for n is equal to k. So we have to assume true for n is equal to k, right? So over here we get a plus b to the k is equal to a to the k plus n k choose 1. A to the k minus 1 b plus k choose 2, a to the k minus 2 b squared plus k choose k b to the k, right? So that's what we're going to do. Now, Omi, what's the last step for induction?
Prove true for n is equal to k plus 1.
Yeah. Perfect. So, show true for n is equal to k plus 1. So we're going to start off with our left-hand side, right? And then we're going to go to our right-hand side, right? So I'm going to do an easy induction problem and then a hard induction problem. So over here we get a plus b to the k plus 1, right? Is equal to, this is our left-hand side by the way, is equal to a plus b to the k times by a plus b. And a plus b to the k is equal to, using our assumption, that, right? So we just substitute that in. We get a to the k plus, oh god, this is going to be annoying. K, choose one. A to the k minus 1 b plus all the way to b to the k, right? Times by a plus b, and if we expand that out, we get our right hand side. So that's a relatively easy problem, right? And basically, after you've done this step, you can literally jump to the last step, because everybody knows it's pretty obvious if you do the expansion, you'll end up with the same thing, right? You can try it yourself if you don't believe me, but trust me, it works. Okay, and now we're gonna move on to our really hard one. Okay, so our really hard one is a to the n minus b to the n is equal to a minus b, a to the n minus 1 plus a to the n minus 2b plus b to the n minus 1, right? So you have to show this is true. Okay, now I'm actually going to see if anybody can actually manage to solve this. So I'll give you guys 1 minute to try to solve this, and then we're going to solve it. Okay, so whoever can type a 1 right now, you're literally a god. But like, yeah, so type 1 when you're finished, because this question was super easy. All right, well, Raja, how do you do it?
Show true for n equals assume true for n equals k, and show true.
No, but like, can you do it?
Yeah, I just did it.
Oh yeah, funny. I don't think Renusha can see. Yeah. Renusha, can you get Cost and quickly add me and join if you want to try this induction problem again? Because you've already done it. Yeah, this one is the one that took him half an hour. It took him about half an hour to do. And then I'll give you guys a homework induction problem. But I don't think anybody's going to have any luck solving it. So once you get to the n is equal to k plus 1, if you have no idea where to start, can you please type a 0? There's nothing's wrong with the audio, buddy. They're doing a question. Do you want to join Cost right now, just so I can know that you joined the group? So just request me on Cost. I sent a link above. Oh, okay, you sent a request? Oh, well done. You just sent one. Alright, so just join and see if you can join. Okay, cool. Just see if you can join, Renusha. Daksh, do you have any idea how to do this? Or have you done it?
I'm getting through it.
Is it?
Yeah, I don't think I'll solve it in
You don't
like a
reckon?
couple
All
of
right,
minutes.
so should we
I
just
need
do
some
it?
time.
Because the solution is actually kind of easy. But can I just, is it alright if I skip the show true for n is equal to 1? Because it's pretty obvious it's true for n is equal to 1, right? So we can just do it for this. So, let's do it for n is equal to, let's just assume true for n is equal to k. So we get a to the k minus b to the k is equal to a minus b, a to the k minus 1, plus a to the k minus 2b, plus b to the k minus 1. Yes? So now let's show true for n is equal to k plus 1. Yeah, remember it took you half an hour? Yeah, this is a nice question. Bro, your solution was nasty, let's be honest. You only like, my solution was better. Let's be honest. Let's be honest. Come on, let's be honest. Be honest with me right now. Come on, Renusha. Oh, hey, I'm the one who invented that solution. Alright, whatever. So, show true for n is equal to k plus 1 is a to the k plus 1 minus b to the k plus 1. Now, this is our left-hand side, right? And 99% of people are going to get stuck here. What do? Let's think about it. We want to get an a to the k minus b to the k, right? So let's say this is a to the k times a minus b to the k plus 1. But I need to get a b to the k, a minus b to the k there, right? So what I'm going to do is I'm going to add, notice here, I'm going to add b to the k times a, and I'm going to subtract the b to the k times a, okay? Now what I'm going to do, so this is 0, by the way, so you can have a look. This is actually 0 because it's the same thing. I'm going to take this, and I'm going to factor out an a. I get a to the k minus b to the k is minus b to the k plus 1 plus b to the k times by a, right? And over here, I can just substitute my assumption, right? So over here, I get a minus b, a to the k minus 1 plus a to the k minus 2 plus a to the k minus 2b plus all the way plus b to the k minus 1, right? Minus, now over here, I'm going to take out a b to the k. So remember, b to the k plus 1 is b to the k times by b. So we can take out a b to the k in common, and we get a minus b. So you can see an a minus b is common between these two, so I can take that out too. And you can see that I'm just left with my last little statement. I get a to the k plus a to the k minus 1b plus all the way plus b to the k minus 1 over here plus b to the k. Sorry, this is plus. This is not minus. Yeah, because you take out a b to the k, right? So this is plus. So plus b to the k, and that's equal to our right-hand side. So can you type a 1 if you understand what I just did there? Frank, are you confused about this? A little? What's confusing you about this one? Hold up, just give me alright, cool. Type a 1 if you were mind blown. Alright, I guess nobody was mind blown. Yeah, it is pretty easy when you look at it. Oh, you got it? Yeah. Yeah, it is a very nice solution. Sorry, I'm just gonna see if I can find my induction homework. Yes, I have one last challenge problem. Okay, so the tute is done. You can leave if you want to, but if you guys want a really, really ridiculously hard question, really, really ridiculously hard, then I'll give you guys one last induction problem. One last one. This one took me, so everybody knows about that n plus 1 on 2 is greater or equal to nth root of n factorial, right? That was the one that I gave, and it took me like, I don't know, like 10 minutes. This one took me about an hour. So, show cos pi on 2 to the n is irrational for all n element of integers. Okay? So, if you guys want to stay and try this, I'll go through the solution at the very end because this is a really, really nice problem. But if you guys want to leave, you guys can leave now. Yeah, good luck. This one is ridiculous. Like, it's actually crazy how hard this one is. Alright, see you, Daksh. Yeah, yeah, that's what I'm saying. So show that cos pi on 2 to the n is irrational. Oh, for all n is greater or equal to 2. Sorry, not n is an element of it, greater or equal to 2. Sorry. Alright. Alright, see ya, Raja. Yeah. If you guys want to try this, you guys can. I feel like only Renusha, who came back from Kumon, is gonna try this. Alright, see you, Frank and Omi. Bye-bye. Alright. First, there's only one page. This is an entire page. Here you go. It's being recorded. It's gonna be up on YouTube if you want to watch it again. There's more if you want to see. There's like all of this, but I'll just send you the YouTube link. I think that'll be easier for you. All right. Cool. I'll just quickly go through the solution. Renusha, have you managed to solve it, or you give up now? Haven't solved it yet? Alright, well, what I'll do is I'll post this as a separate video for a solution. I'll give you guys an entire night to try to solve it. Renusha, message me if you've solved it, because it's actually ridiculous, bro. Alright? If you want a hint, it's just make sure you know your trig identities. Otherwise, this is legitimately impossible. Okay? And I know you know them, so yeah. Like, try it. Alright? Talk later, bro. I'll send you the video too for this thing if you want to watch it. I don't think there's much. Like, is there anything here? Like, I'll show you some stuff that we've covered. Just tell me, is there anything here that you want to rewatch? So over here we have tree diagrams, coin toss, modular arithmetic, tree diagrams, multiplicative and additive laws, how many permutations and combinations. Do you want to watch this video? Because I can send it to you. But I'm pretty sure you know most of this. We've done binomial expansion and stuff. Or you want it? I can send it because, yeah, it's easy. Alright, cool. I'll send it to you then. You can watch it if you want to. You don't have to. Alright, cool. I'll talk to you later then. Bye-bye.